Up to last class, we were looking at so-called what is known as the concept of sigma algebra properties, and then the special sigma algebra on R, what is known as the Borel sigma algebra. Right. Now, today we are going to see what is known as monotone class. So let's begin with the definition. So a family script A of subsets of omega is called a monotone class. If it is closed under monotone operations. What are they? That is, so if you have an in A, right, for each n in n, and an increases to A, and it is increasing. So that will imply that A belongs to A. And second one, similarly, if you have a sequence of sets which are decreasing, and if decreases to A, that will again should imply that A belongs to A. Yes. So these are the two conditions. Fine. Yeah. So let's begin with the lemma. First one. Every sigma algebra is a monotone class. Yeah, this is why is this true? In fact, why is this true?
Closed under countable union.
Yes. So sigma algebra is always closed under countable union and countable intersection. And whether it is so, how does it help us? What is A in this case? Well, if at all, if you have an increasing sequence, right? So if you have an is an increasing sequence, and if an increases to A, then what is A?
Supremum of an.
Yes. So what is the supremum? Can you be more precise?
Union.
Ah, right. You are right. Repeat. Yes, Manish.
Unions.
Ah, yes. Union over n and n. Yeah, this is exactly the limit. And similarly, if an is a decreasing sequence of sets, and if decreases to A, then what will be A? It's the infimum, which is intersection over n and n. A. And we know that if you have a sigma algebra, and if you have a countable number of sets, or if you choose a countable number of sets from the sigma algebra, then their union and intersection, they are again in the sigma algebra. Therefore, it is a monotone class. Fine. Right. because I'm not going to give a proof. It's only you who is going to write a proof on your own. So therefore, I'm just giving it orally. Right. Next one. If A is an algebra, if you have an algebra, then A is a sigma algebra if and only if A is a monotone class. How do you show this? Well, one part is clear. You don't have to. If it is a sigma algebra, then it is a monotone class. There is nothing to prove. Fine. But how about the converse? Converse. If you have a monotone class, okay, so we saw something yesterday. What was the last exercise that was given? In fact, last lemma that we proved. In fact, stated. I did not prove. What was the last one that we stated yesterday? Just look at your notes. Just look at your notes. What was the last one that we did?
We can replace a countable number of union of sets by its disjoint countable union type. Maybe we can define a sequence like A1 line, then A1 union A2, A1 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 union A2 A union.
So for the converse, what you do is, well, you don't need even that part. So for the converse, what you do is that you choose form a different sequence. Bn is union k running from 1 to n, an. So now notice that Bn is an increasing sequence, and that should help you. Yeah, this is the hint. So form this, and then that should tell you. Yeah. So proof, I'll simply say exercise, which you should be able to. So here is the hint. Use the hint. So in the case of monotone sigma algebras, what are the other results that we proved? What are the other results? What are the other results that we proved for sigma algebras? apart from examples and definition?
It is closed under countable intersection.
And then?
And it is also closed under subtraction. I mean, if E and F are
And
two
then
sets.
next one.
Then what we did was, if we have two algebras, sigma algebras, then their intersection will also be a sigma algebra.
What is the main result that we proved there? What was the main thing?
Smallest sigma algebra containing
Existence of a smallest sigma algebra containing a given collection. So next natural question here is that, given a collection, do we have a smallest monotone class containing that? What is the answer? Yes, how did we prove there? First, what was the first lemma that we proved there in the case of sigma algebras? How did we prove there? What was the first result that we proved in this direction?
Intersection of two sigma algebra is again a sigma
Intersection
algebra.
of two sigma algebras is again a sigma algebra. So let's do the same thing. So let me begin with a lemma. So I'll put it as 1. So intersection of two monotone classes. Is again monotone class. Yes, start proving. Start. If you are finished, please raise your hand.
So, sir, can you please show me the definition for monotone class? I was actually late a few minutes. Oh, thank you.
Welcome. If you have finished the proof, then please raise your hand. Having done lots in the case of sigma algebras, I think all these should be easy. Therefore, I thought I'll just leave it to you all.
Sir, what does this up arrow and down arrow means?
Increasing, decreasing.
Okay.
So if you have an increasing sequence of sets and if it increases to A, then A should belong to A. If you have a decreasing sequence of sets, and if it decreases to A, then the limit A should also belong to A. That's the whole thing.
Okay. Got it.
Is it done? Yes, others. Is it so difficult that you can't even try? Ankit, Anu, Anupam, Hariprakar, Ashish. Sushil, Saurav, Rahul, Nirmal, Meenakshi, Manoj, Manish, Mahesh, Govind, Gopal, Geetanjali, Deepak, Vishwaprakash, Atharva. Try to be fast. More or less the same proof. Is it done? Okay, fine. So on the belief that you will be able to, I am proceeding further. Yes, next one. Arbitrary intersection of monotone classes is again a monotone class. Third one, yeah, this you should be able to, same proof. Yes, so now last one, given a collection script S of subsets of omega. There exists a smallest monotone class M of S containing yes. Yes, how do you prove this one? First thing is the at least does there exist at least one monotone class containing yes?
Sir, that will be the smallest sigma algebra itself.
Exactly right. The sigma algebra itself. Right. Fine. And then how to produce a smallest? How to produce the smallest?
All the monotone classes containing S and then intersection them.
Take the collection of all monotone classes containing S, take their intersection, that's it. And that is going to give you the smallest one. Yes. Fine. So you all should be able to write the proof by now. Right. Fine. So now if you have a collection of subsets, this is collection of some collection. Subsets of omega. Then I have one is sigma of S, the other one is the monotone class. And in fact, monotone class is always contained in the sigma algebra generated by this. Right. Now, if I have an algebra, this is an algebra of subsets. And therefore, again, these two make sense. Because M of A in general, it need not be an algebra. Because M of S, it's not an algebra in general. But we do not know, in fact. So the next one says, gives a relation between MA and sigma of A whenever A is an algebra. So this is what is known as monotone class lemma. Let A be an algebra of subsets of omega. Then the sigma algebra generated by M is same as the monotone class generated by A. The sigma algebra generated by A is same as the monotone class generated by A. Yes. The proof is not a difficult one. It requires some minimum set of patience. Only this much. It's not that difficult. Fine. Yes. How to show that these two are equal? How to show that these two are equal?
We shall show that sigma of A is contained in monotone class of A.
Right, that's right. That's what we are going to do. But how to proceed? Where to proceed? Out of the results that we proved today. Right. So let's look at. See, if you have an algebra, then it is a sigma algebra if and only if it is a monotone class. Now, I have a monotone class. If I can show that this M of A is itself an algebra, what will that prove? What will that prove?
It would be sigma algebra also.
M of A is a sigma algebra. And once you know that M of A is a sigma algebra, it's a sigma algebra containing A. And therefore, sigma of A will be contained in M of A. That will prove what we wanted.
Yes, sir.
So we are going to do this. So well, we'll start with, yes, so since M of A is contained in sigma of A, it is enough to show that sigma of A is contained in M of A. Right. Now observe, in order to, so observe that in order to prove the above inclusion, it is enough to show that M of A is an algebra. Once you show that this is an algebra, it follows that it's a sigma algebra. And because sigma of A is the smallest sigma algebra containing A, you get that sigma of A is going to be contained in M of A. Fine. Right. Now let's show that. Right. Okay, so claim is that this M of A is an algebra. Right. Yes, what are those things that we wanted for an algebra? You know why one in general chooses morning classes?
Empty set belongs to their closed under complementation and closed under finite union.
Right, very good. So how many of you are aware of this fact that the reason for choosing a morning class, early morning class? How many of you knew this? For choosing a reason for choosing an early morning class? The reason being, students will be fresh. But I couldn't see any freshness except a few. Right. So how do you show that it is an algebra? So first thing, so three things that we wanted is that it is closed under, sorry, it has got the empty set, and then it is closed under complementation, and then it is closed under
Finite union.
union. Finite union, right. So if we can show these things, then we are done, right? Yes. So empty set belongs to that. Why?
We can take sequence of empty sets.
Sequence of empty sets.
It is empty set.
First thing, it should have an empty set, right?
Yes.
Ah. Then you can choose a sequence of empty sets. If it has an empty set, then there is nothing. Then only then you can choose.
Sir, the given A is already an algebra. Hence
Exactly. So given that A is an algebra. So that implies that empty set belongs to A, which implies that empty set belongs to M of A. And we are done. First condition. Second, complements. Right. So, yeah, so this is one of the famous tricks, especially in this kind of set theory. So I'll form MC. What is this one? All those E in M of A such that E complement belongs to M of A. Yes. Is it non-empty?
Yes, sir.
Yes, sir.
Yes, sir.
Is it non-empty? Why is it non-empty?
Sir, because phi belongs to A, I mean phi belongs to MA, and its complement omega is also. We can take a sequence of omega and hence.
Sequence of why again and again sequence? Why again and again sequence? Yeah, so first thing, observe that the whole sigma algebra is contained in MC. Whenever E belongs to A, then E complement also belongs to A, and A is always contained in M of A. And that tells you that A is contained in MC. And hence, this MC is non-empty. So I have a non-empty collection. Fine, first one. Next one. Now, yeah, we are going to show something that this is a monotone class.
Sir,
Huh?
sir, here A complement will be phi.
A complement will be 5. What does that mean?
Means how we are claiming that that A will be contained in MC.
Huh? What is A?
An algebra.
Huh? Algebra, it's a collection of subsets, which means if E belongs to A, then E is contained in MC. E belongs to MC. That's what I wanted to say. That's what I wanted to say. How does this follow? E belongs to MA. Sorry, E belongs to A, which is contained in MA. Implies now E belongs to A. That implies that E complement also belongs to A because it's an algebra.
Got it, sir.
Huh?
Got it, sir.
Right. So that's exactly. This is the idea. Fine. Right. So why is it a monotone class? So let AN be an increasing sequence of sets from MC such that AN increases to A. So we will have to show that A belongs to MC. How do you show that A belongs to MC? How do you show that A belongs to MC? It should first thing A should belong to MA and its complement should also belong to MA. Yes. Is that clear? So since MA is a monotone class, it follows that A belongs to MA, right? Further, A complement. What is A complement? It's the complement of this union, which is same as intersection over N in N, AN complement, right? But ANs, where do they belong to? ANs, where do they belong to?
MC.
In algebra,
Huh? Algebra. ANs. ANs is an increasing sequence of sets from MC. So ANs, they belong to MC and therefore AN complements, where do they belong to? So ANs, they belong to MC and therefore all these ANs, they belong to MA, and because ANs, they belong to MA, AN complements, they also belong to MA. The way we have defined MC, that tells us that AN complements, they also belong to MA. So since AN belong to MC for all N in N, implies AN complement belongs to MA for all N in N. And that will imply that intersection over N in N, AN complement. What can you say about this one? This intersection.
Belongs to MA.
Where did this belong to? Okay, so is it a decreasing class?
Yes, sir.
Why is it decreasing? So as ANs are increasing, so AN is contained in AN plus 1 for all N in N, implies AN complement contains AN plus complement for all N in N. That is, AN complement is a decreasing sequence. So which will imply that AN complement, well, intersection. Where N in N, AN complement belongs to MA. That is, A complement belongs to MA. So we have shown that both A as well as its complement belongs to MA. Similarly, MC is closed under MC, if AN is a decreasing sequence, of sets from MC, then MC such that AN decreases to A, then A belongs to MC. Yeah, so these are the, so this I'll leave it as an exercise. So which means that what have we shown? We have shown that MC is a monotone class. So what does it tell us? What did we prove by showing that MC is a monotone class?
It should contain the smallest monotone class, ME.
Exactly. So thus MC is a monotone class containing A and hence contains MA. On the other hand, it is clear from the definition of MC that what is that is clear that MC is contained in MA. Therefore, MC equal to MA. That's it. What does it tell us? MC equal to MA.
That MA is closed under complement.
Exactly. Yes. MA is closed under taking complements. Right. So one thing we have done. So we have shown that MA is closed under complements. Fine. Next one. What is the next one? We will have to show that it is closed under finite union. So, well, it's enough to prove it for two sets. Fine. Now, again, we are going to make use of the same idea. Now, what you do is for, why this now? E in A. So let me write ME as all those F in MA such that E union F belongs to MA. Right. So first thing to be observed that, yes, what was the first thing that we did? here. So observe that this A is contained in MC. Same thing. Non-empty. Is it non-empty?
E belongs to
Yes, E belongs to ME.
A is contained in ME. A itself is contained in ME, the whole. And hence ME is, sorry, ME is non-empty. It's a non-empty collection. Second thing. What was the second thing that we observed there? Well, this is a monotone class. This ME is a monotone class. It's quite easy for me. You will have to write. I don't have to write. Why is it easy for me? A quick guess should help you. Because it is just an exercise. Right? So verify it and then remaining things. So once you have shown there it is a monotone class. So therefore this is a monotone class contained in MA and it also contains A, therefore ME should be same as MA. Therefore ME equal to M. Yes. Right? Yeah. So fine. So remaining will prove it in the next class. I don't have much things, but still, I don't want to rush through. Right. So next class we'll finish this monotone class, and then we should be able to start with what is known as abstract measures. Yes. Let me stop here. Thank you all.